Welcome back, listeners, to another enlightening episode of Operating Systems Crashcast. I'm Victor, and with me as always is the brilliant Sheila. Today, we're diving into a crucial aspect of deadlock management, deadlock detection.
That's right, Victor. We've previously covered deadlock prevention and avoidance, and now we're exploring how systems can identify deadlocks when they occur. This is a vital skill for any OS engineer or developer to understand.
Absolutely, Sheila. Let's start with the basics. Deadlock detection is a method where the operating system periodically checks if a deadlock has occurred and, if so, takes steps to recover from it. Unlike prevention or avoidance, detection allows deadlocks to happen but aims to resolve them after the fact.
Exactly, Victor. It's like having a traffic controller who doesn't prevent gridlock, but instead identifies when it happens and then directs cars to back up and clear the intersection. Now, to detect deadlocks, the system uses what's called a resource allocation graph. Can you explain that for our listeners?
Certainly. A resource allocation graph is a diagram that shows how resources are currently assigned in the system. It uses two types of symbols, circles for processes and squares for resources. Arrows from a resource to a process mean it's been allocated, while arrows from a process to a resource show that the process is requesting it. If this diagram has a loop, it might indicate a deadlock.
That's a great explanation, Victor. Now let's dive a bit deeper into the detection methods. There are two main scenarios we need to consider: systems with a single copy of each resource and those with multiple copies. Let's start with the simpler case of single copies. How does that work?
For systems with a single copy of each resource, the detection is relatively straightforward. We can use the resource allocation graph directly. If there's a loop in the diagram, it means there's a deadlock. This can be determined using a method that's like following a trail of breadcrumbs through the diagram.
Excellent point, Victor. Now let's move on to the more complex case: systems with multiple copies of each resource. This scenario is more common in real-world systems, but also more challenging to detect deadlocks. Can you walk us through this approach?
Certainly, Sheila. For multiple copies, we use a variation of the banker's algorithm we discussed in deadlock avoidance. The system keeps track of several pieces of information, available resources, maximum needs of each process, current allocations, and remaining needs. The approach works by trying to find a safe order of processes that can complete without causing deadlock.
That's right, Victor. The system repeatedly looks for a process whose resource needs can be met with the available resources. If found, it temporarily assumes that process finishes and releases its resources. This continues until either all processes are accounted for, no deadlock, or no eligible process is found, deadlock detected.
Exactly, Sheila. It's worth noting that this approach takes more time as the system gets bigger, especially with more resources and processes. This brings us to an important question. How often should deadlock detection be performed?
That's a crucial point, Victor. The frequency of deadlock detection is a balancing act between system responsiveness and efficiency. Running the detection too often can slow down the system, especially in large setups with many processes and resources.
Indeed, Sheila. In practice, the frequency might depend on how likely deadlocks are in the system. For example, a system where deadlocks rarely happen might run detection less often or only when certain conditions are met, like high resource use or long wait times for processes.
That's a great point, Victor. Now, let's discuss some advantages and disadvantages of deadlock detection compared to prevention and avoidance. One clear benefit is that it allows for more efficient use of resources since it doesn't restrict resource requests ahead of time.
Absolutely, Sheila. It's more flexible and can work in situations where we don't know resource needs in advance. However, a significant drawback is that detection doesn't stop deadlocks from happening, which means there's always a risk of system hang-ups or the need to stop some processes to resolve deadlocks.
You're right, Victor. And that brings up another important point: recovery. Once a deadlock is detected, the system needs to break it. This usually involves stopping one or more processes or taking back some resources, which can disrupt the system and user experience.
Excellent point, Sheila. In real-world systems, deadlock detection is often used alongside other methods. For instance, a system might use some prevention techniques for critical resources avoidance for predictable scenarios, and detection as a backup for unexpected situations.
That's a great summary, Victor. As we wrap up, what would you say are the key takeaways for our listeners, especially those preparing for interviews or real-world OS development?
Great question, Sheila. I'd say the main points to remember are: understand the basic idea of deadlock detection and how it differs from prevention and avoidance. Know the approaches for both single and multiple copy cases. And be aware of the trade-offs involved in using deadlock detection, particularly regarding how often to check and how to recover.
Excellent summary, Victor. I'd add that it's crucial to understand when deadlock detection is appropriate. It's particularly useful in systems where deadlocks are rare but potentially costly, and where we need to maximize resource use.
Absolutely, Sheila. Well, that brings us to the end of today's episode on deadlock detection. We hope our listeners found this informative and engaging. Thank you all for tuning in to Operating Systems Crashcast.
Indeed, thank you all. Remember to keep exploring these concepts, as understanding deadlock management is crucial for any aspiring OS professional. Until next time, happy learning.